With that little chat, we're going to start. So welcome everyone to day 2 of the UKESM General Assembly. Today is Contributed Talks. This is session 1. My name is Colin Jones. I'm going to chair this session. Just a reminder of the ground rules, please mute your microphone while you're online. If there seems to be a problem with bandwidth, occasionally we found disabling your video can help as well. We'll have a chat where you should pose questions. I will then try and give to each speaker a couple of questions in the 2 minutes we have, or the time we have. If we don't manage to do all the questions, we'll put them into a Google Doc, and then hopefully the speakers can respond later to you, either during the day or afterwards. The talks are 8 minutes in length plus 2 minutes questions. If you're shorter than 8 minutes, you get a bit longer for the questions. And we will have to keep the time as much as possible. Hazel will do the timing, and she will tell you when you have 2 minutes left to speak. So with that, we'll go straight ahead to talk number 1, which I believe is Catherine Hardacre from the Met Office, talking about evaluation of the sulfur cycle. Catherine, over to you.
Thanks, Colin. Good morning, everyone. This is a very brief overview of the work I've been doing to evaluate sulfur dioxide and sulfate in UKESM 1. Okay. Just a bit of a delay going to the next slide. Okay, so the background to this work is that sulfur dioxide, or SO2, has a variety of natural and anthropogenic sources. And once it's emitted into the atmosphere, it is oxidized to form a sulfate aerosol, which has a number of roles. It's involved in acid deposition, atmospheric aerosol loading, and cloud properties. So it's important for the Earth's radiative balance. And in order for a model to represent the Earth's radiative balance well, we need to have a good representation of these processes in our model. So if we look at the bar chart on the top left-hand side there, we can see that the global trend for SO2 emission has been to declining emissions over the past few decades, but there are some regional variations to this trend. So if we look at the bottom 2 time series plots for Europe and North America, the black line shows the observed SO2 emissions, and we can see that emissions in these regions have declined due to legislation over the past few decades. But if we look at East Asia in the top right-hand plot, we can see that emissions have at best plateaued and might be increasing slightly. So again, if we want to be able to have confidence in our future projections of the Earth climate, we do need to make sure the model can capture these historical trends. Okay, for this piece of work, I've been using 2 observational ground-based data sets to evaluate the model against. So the first one is CastNet, which is a American network, and we've divided those sites up into the eastern sites, which are more polluted, and to the western sites, which are cleaner. And we've got measurements of SO2 and sulfate from that network. And then for Europe, we've been using the EMAP network, which again, we've got SO2 and sulfate for. And then for the model, we've been using 4 members of the SMURPHS historical ensemble that was run for UKESM 1. And that's the fully coupled model with strap top chemistry and the glow-map aerosol. And we're looking at a period from about 1987 to 2014, which is where we've got overlap between the model simulations and the observations. Okay, this is an overview of our results so far. In the top row, we're looking at SO2 concentrations, surface concentrations. The middle row, we're looking at surface sulfate concentrations, and the bottom row, we're looking at SO2 dry deposition, which is available from the CastNet network. For each plot, we're looking at the model in blue and the observations in black. Each time point represents a mean across the network in the shaded region, and the bars represent the standard deviation across the region. We've got CastNet West on the left, CastNet East in the middle, and then EMAP on the right-hand side. Okay, so you can see that UKESM is able to capture the long-term trends in all of these parameters, but that there are biases. So for the surface SO2 concentrations, the model overpredicts SO2 in all of the regions that we looked at. So for both the polluted regions and for the cleaner CastNet West region. For the surface sulfate concentrations, the model underpredicts sulfate in the polluted EMIP and Carcinet East regions, but there's a slight overprediction in the Carcinet West region. And then for dry deposition, the model slightly overpredicts SO2 dry deposition, which is likely due to the fact that we've got too much sulfur dioxide at the surface. Okay, for the next set of results, I'd like to show some of the evaluation we've done to the model where we've improved the dry deposition process. So the reason for these modifications to the SO2 dry deposition process, as Jane mentioned yesterday, is to try and address this cold bias that UKESM has in the mid-20th century. So the time series here is the historical period with showing global mean surface air temperature for UKESM in blue and observations in black. And you can see that there's a definite cold bias in the mid-20th century. So a number of modifications and bug fixes were made to the SO2 dry deposition process. I won't go into them right now, but they have the they all act to increase SO2 dry deposition. So more SO2 is removed from the atmosphere, leaving less available for conversion to sulfate. Okay, and this is the same series of plots I showed earlier, but with the addition of UKESM with the SO2 modifications in red. And if we look at SO2 concentrations, we can see that as intended, we have reduced SO2 concentration at the surface, at the regions that we've looked at, and it has decreased our positive bias. In terms of sulfate, again, as intended, we've reduced sulfate concentrations at the surface, but at the polluted sites at EMIP and Carcinet East, that does increase our negative bias. Although at the cleaner Carcinet West sites, it does reduce our positive bias. And then for SO2 dry deposition, again, as intended, we've increased the rate of SO2 dry deposition, and it has driven, it has acted to increase our positive bias in SO2 dry deposition. So, thanks, Hazel. Work in the future will be to address some of the reasons for these biases and why they've increased and decreased. So we'll be looking at greater temporal and spatial resolutions, as well as the emissions and transport processes to try and address some of these biases. And then the final set of results I'd like to show is a very initial set of results. We'd like to use satellite data to evaluate the model. And Richard Pope at Leeds University has had an initial look at a new product from OMI for satellite SO2 concentrations. So this product has been developed by some people at NASA, and it's available from 2005 to 2014. So we're looking here at UKESM on the top row, the OMI product in the middle, and then UKESM sorry, the difference on the bottom row. And then we've got DJF on the left and JJA on the right. So what we can see here is that the OMI data is quite noisy in the higher northern latitudes in their winter, and also in the lower southern latitudes in their winter. And that's driving quite a large negative bias in the UKESM model. However, Richard thinks that we can address some of this if we screen for the solar zenith angle and perhaps use an annual mean rather than the seasonal means. However, he is confident that the positive bias we see over the polluted Eastern China region and India is a correct result. So we'll be doing a bit more on this to try and develop a good evaluation using the satellite data. Okay, thank you.
Okay, thank you, Catherine. Right, there's a couple of questions in the chat. I'm going to precede them with one very quick one, and then come to those three. So the evaluation is surface SO2 and SO4. So is there any way to evaluate, apart from with satellite, which you've indicated, some way to evaluate non-surface, i.e. above the boundary layer, let's say, at point observations?
I probably need to have a look through the literature and see if there's any, I don't know, aircraft data or anything like that. I haven't explicitly looked for it, but there might be some out there. If anyone does know of any, please let me know.
Okay, and then to follow on from that, a question from Till: what would you do to change the model simulations to increase the SO4 concentration while keeping the SO2 concentrations low, or are there aspects of the conversion SO2 to SO4 that are not working perfectly?
Yeah, we think there might be, the model might not be representing the oxidation particularly well, and that could be because we're not capturing the oxidation of the oxidation of SO2 correctly, or the oxidants, so ozone, might not be represented correctly. So we're going to look at that in later on in the year. We've got plans to investigate that in more detail.
Okay, follow up from Stevenson. The main route within cloud is in cloud plus H2O2 oxidation. Do you know if that looks okay compared to other models, possibly?
I don't know if it looks okay, but we'll put it on the list of things to have a look at when we investigate the chemistry in more detail.
Okay, I'm going to ask one more, and then the others will have to be popped into the Google Doc for later. There's a question: are the OMI data columns any influence of clouds on the data? Is the cloud contamination on the satellite data?
Okay, so I'm not a satellite expert. I probably have to get back to you. There probably is. I know that they've had to do quite a lot of work to get this SO2 product as something useful. Yeah, for details, I'll probably have to get back to you on that. I'll have to do ask Richard and check up on the information for the product.
Okay, great. So the other ones we'll transport to the Google Doc, and please have a look yourself, Catherine. We're going to move on now. Thank you, Catherine. Next up is Nicolas Bellouin from the University of Reading. Are you ready to roll, Nicolas?
I am, yes.
Okay, welcome. Over to you.
Okay, can you hear me okay now?
Yes, I can hear you. Yeah.
Great. Okay, so what I'm going to talk about is bounding aerosol forcing of climate change. So that's very much a collaborative work with all the people that you see on the picture. To give the context,
Nicolas, you're breaking up a little bit. You might want to try without your video on, just to see if it helps.
Okay.
Sorry.
Okay, let's see if that works better.
Sounds good at the moment. Yeah.
To give a little bit of context, so it all started with a workshop in early 2018 at Ringberg Castle in Germany, and then it took us about 2 years to get the review paper accepted. And during those 2 years, there was a lot of discussions, a lot of drafts, and so there was a lot of thinking put into that work by many people. So what we've done is decompose the aerosol forcing problem into 3 different problems. One is what are the industrial era changes in aerosol optical depth and cloud droplet number. Second is what is the sensitivity of top of atmosphere radiation, atmospheric absorption, and clouds to those changes. And finally, and importantly, what are the fractions of the globe where different radiative forcing mechanisms are exerted. And then we use the published literature to essentially quantify those 3 aspects. So in that sense, the work is more an assessment than a review. The results are here in that table, so results of that quantification, and all the details are in a fairly dense paper. But here I want to draw your attention to see the last column of that table, which shows which lines of evidence have been used for the different aspects of aerosol radiative forcing. And you see that global modeling, like UKESM, is often represented. So that doesn't mean that global models are the strongest line of evidence all the time, but rather that perhaps stronger lines of evidence like LES or aircraft observations, it's difficult to average them into a global average, whereas global models of course, that's their main function, right? They are integrators of this kind of things. You can also see that there are mechanisms in which global models have not been used, and that's aerosol cloud interactions, and especially rapid adjustments to aerosol cloud interactions, so changes in cloud thickness or changes in cloud fraction. And here that's because there's been several studies that have shown that global models essentially struggle to get the correct signs of those adjustments. So they cannot really be trusted as a line of evidence for those mechanisms. Oh, sorry, I went one slide too far. So this is the results that we got. So that's the probability distribution function of aerosol radiative forcing. In black, this is the assessment of the fifth assessment report of the IPCC in 2013, and in blue, this is the assessment of the Ringberg review that I'm talking about for effective radiative forcing. And you see that essentially the story is the same in the two, even though the approaches are very different. One thing that is quite clear on those probability distribution function is that from physical arguments alone, it is essentially impossible to bound the negative end of the aerosol radiative forcing distribution. Mostly because of uncertainties in rapid cloud adjustments. So to provide additional bounds, we needed to use alternative approaches, and those are top-down approaches or observational inferences. That is to use observed global temperature change or global dimming and brightening trends to provide additional constraint on the forcing, and that's the colored section here, which are essentially excluded by those top-down approaches. And so you end with a very with a likely range of about -0.6 to -1.6. Interestingly, all SMURPHS models fall into our assessed range. And I think that's and that range is narrower than for SMURPH5, and I think the reason is that a lot of SMURPH6 models essentially apply their own top-down approaches for ERF, either tuning ERF to observe global surface temperature change, or tuning aerosol ERF to get the right sign of anthropogenic ERF. That's the case for UKESM1. At first, the aerosol forcing was about -2.4, I think, and then it's after several correction, it went down to -1.45 in the current version of the model. So the paper tries to end with some positive notes of promising avenues for progress. So like Fiona noted yesterday, scale effects are important in aerosol radiative forcing.
2 minutes.
Thank you. And by scale effects, we mean the problem of resolution, of course, but also the problem of covariations, covariability between the cloud field and the aerosol field, which means that local responses are not always representative of responses average over the cloud field. A lot of progress has been made using tracks, volcanic tracks, ship tracks, factory tracks, city tracks, to understand the response of liquid cloud to aerosol perturbations, and there's hope that the same progress can be done with ice clouds, which remain a big question mark. We don't know much about ice cloud responses to aerosol perturbations, although at the same time, so we don't have any strong evidence that there has been any response of ice clouds on a large scale. Observational inferences, so top-down approaches are promising, and indeed we need them to provide strong bounds on the relative forcing. But the uncertainties are not well understood, especially their dependency on the assumed history of the aerosol forcing, which is very uncertain. There are very large trends in aerosols, like Catherine just noted here as a trend in optical depth over the past 15 years or so, and you see very strong increase over India and very strong decreases over China. That could be used for this kind of observational inferences. And finally, PPEs have been really useful to better understand parametric uncertainties in models, and hopefully there will be ways to also include the structural uncertainties into this kind of statistical consideration. So that's it for me, and I welcome your questions. Thank you.
Okay, thanks, Nicolas. And I think we established in the chat it's me that's cracking up, not you. So okay, well, can you hear me now?
Yes, I can hear you.
Okay, good. Right, I'll kick off with a question. So one of the cloud types that have been shown to be important for at least for the equilibrium climate sensitivity response in our model and potentially in the NCAR model is supercooled liquid clouds and their response to warming. So what emphasis has been placed from the context of aerosol forcing on supercooled clouds, which are sort of, as you know, they're a mix of liquid and ice clouds? Is there something particular that we need to address there?
So there are studies that indicate that supercooled liquid clouds tend to respond in similar ways to liquid clouds, to warm clouds. In that sense, the presence of an ice phase, for example, doesn't seem to change the response too much. But that's still a question mark in the response of those type of clouds. Often the track analysis that have been used to look at cloud responses in warm clouds have been restricted to warm clouds for various reasons, so they need to be extended to supercooled clouds. So yes, there is a question mark there.
Okay, a question from Chris. We've learned a lot from perturbations like volcanic eruptions. What do you think are the prospects for evaluation in the context of aerosol forcing following the COVID lockdown and change in emissions?
So there have been several teams looking at that already, and the indication is that lockdown perturbation is not as big as you would expect, mostly because a lot of sectors have not been affected by lockdown. So lockdown has mostly affected transport emissions, but domestic heating and power generation, for example, haven't been affected that much. So I think there's a French study that estimates that the perturbation to a PM in Europe was only 5 to 10%. So it's very small signal. So it's, having said that, there are indications that maybe we can see something in aerosol optical depth over China, especially transported over the sea, over the Yellow Sea. There might be statistically significant perturbations, but the signal seems much smaller than the eruptions that have been used in the past.
Okay, great. I think with the switch of slides, I'm getting told that I need to move on. So there are a couple more questions in the chat and comments. If you could take a look, Nicolas, and maybe respond to those offline. Yeah. So thank you. We're going to move on to Gerd Folberth. Gerd, are you ready to present?
I am. Can you hear me reasonably well?
I can hear you excellent. Yeah, so you obviously got better headphone than I have. Over to you, Gerd.
All right. Thank you very much, Colin, and good morning, everyone. I will show you today some details and some first results from a configuration that we've put together that is emissions-driven for methane rather than concentration-driven. So let me try to advance the slide. Yeah, perfect. So just to give you a few details, we've produced this methane emission-driven configuration, just switching from surface concentrations to emissions in the release job. So that means we've turned off the prescribed surface concentrations for methane, and we're using anthropogenic emissions for methane from SMURPHS. And we are also using an interactive wetland model that produces the natural part of the methane emissions. So in that sense, the natural emissions are completely interactive. So I think it's worthwhile noting that we simply switched from a concentration-constrained configuration to an emissions-driven configuration. So there hasn't been any tuning or recalibration done so far. And in view of that, actually, the model does perform quite well, as you can see on the plot here. So what I'm showing is the concentration constrained configuration in black, and the emission driven in red, which is a convention that I will use throughout my presentation. And the two configurations agree remarkably well for the first 70 years or so. And then at the point where anthropogenic emissions become important, the two configurations start to diverge, and that ends up at sort of present day level in 2014 with about a 20% low bias in the emission-driven configuration. At the moment, we don't know whether this is due to the emissions in SMURPHS or due to the methane lifetime in our emissions-driven configuration, but that's something that we'll have to work out in the near future. There's certainly a few things that we need to improve on that configuration, but still it has already produced some very interesting results, which I'm going to go into now. And one of them is we've run, apart from running a number of historic ensembles, we'll also run two future ensembles, scenarios rather. They're not ensembles yet. And I want to focus on the aggressive mitigation scenario, which is the SSP1 2.7. So in this scenario, there is a very aggressive mitigation assumed for methane, as you can see. And in that scenario, so focusing on the red line and focusing on the dot-dashed red line that decreases in the future, you can see that the concentrations and indeed the atmospheric burden of methane drops to a level that was last seen around the early parts of the 20th century, around the 1910s or so. So this would suggest that this mitigation strategy would allow us to recover to an earlier point in time, which is unfortunately not the case, because when you look closer, while the burden and the concentrations do indeed return to levels that are earlier in the industrialization period, which is good in terms of radiative forcing, the methane cycle itself hasn't actually recovered at all. So the emissions are still a lot higher than they were in the early part of the 20th century, and also the sinks are a lot higher than they were during this period, which seems to indicate to me that what happens is that due to factors that we'll need to investigate further, the methane turnover or the cycle has just simply sped up quite a bit in this scenario in the future. This can be potentially connected with what other co-emitted pollutants do, like NOx or other species, but we'll have to look into that in more detail. We haven't done so far. It's interesting to see, though, that recovery, as is usually thought of, isn't happening, and the methane cycle in this case stays quite perturbed. Another interesting result that I am particularly interested in is the methane hiatus seems to be reproduced by the model. So let me just walk you through a little bit on what's shown here. I've basically, in this slide, I've summarized the methane budget from our historic run with the methane emission-driven configuration. From left to right and top to bottom, you see all the sources, the sinks, the burden, plus the net atmospheric flux, and the methane surface concentration again. And there is this period between late 1990s and the early years in the 21st century where the methane growth rate has experienced a slowdown and indeed a hiatus. And that seems to be represented in our model. Now, from a very quick and superficial analysis of our budgets, it can be concluded that this may have been driven by the anthropogenic emissions. Because what we see here is that while the methane sinks, indeed mostly the reaction with OH, continuously increases over the entire simulation period, there is a slowdown in the emissions in the period before the hiatus from about 1980 to 2000. And
2 minutes.
that, thank you. And that turns into a decreasing and indeed almost slightly negative net atmospheric flux from methane around 2000. And this slowdown in the anthropogenic emissions may have economic and political reasons. I mean, there's the oil crisis and there is the collapse of the Soviet Union. So it's going to be interesting to look into these things in more detail, but I think it's promising to see that the model on its own, without being constrained by observation, is able to reproduce this behavior from the input. And then finally, I just want to give you an outlook on what else is going on in this space. So Fiona mentioned yesterday, or I think Fiona mentioned yesterday, that there is a CO2-driven configuration produced and run by Spencer Liddycott. And so Spencer and I decided to try and merge our two configurations to produce a completely emission-driven configuration, which is what I'm showing here. And in all these plots, the CO2 and methane emission-driven configuration is shown in cyan. And basically, we've only done a pre-industrial control run so far, but the idea was to see whether it works or whether it behaves completely bonkers, which, by the way, is a technical term. But it looks like everything is more or less fine. The net radiative flux is well under control, and all a couple of other important diagnostics show green light, basically. So this is where we are with this configuration, and hopefully we can do more science with this in the near future. Well, I think that's all from my side, and thanks very much. And I'm happy to answer any questions if there are any.
Okay, thank you, Gerd. Yeah, I can see 3 in the chat. I'm going to go in reverse order this time. So PMC 205, that might be Peter Cox. Where do the methane anthropogenic emissions come from? Could they have been derived in part from the atmospheric concentrations, or are they completely bottom up?
Again, I'm showing lack of knowledge here, but they are, as far as I know, at least for the historic period, they are partly derived from the measurements, as far as I know. So there's information about the measurements pulled into these emissions, as far as I'm aware of. Okay, and just for clarity from me, wetland emissions are internally prognosed in this model, are they? Yes, that's correct. So it's the wetlands are fully active, and part of the wetland model is a methane emission scheme that we are using. So the methane emissions are also internally consistent with climate and everything. Okay, question from Graham. Is there any plan to investigate the Pinatubo impact on methane growth rates through the 1990s? And he refers to a paper. Well, now there is. Okay. One quick last one. I'm sorry, there's a number in here. I'm going to give one quick last one from David Stevenson. Oh, another one's just popped up.
I think the difference between the concentration-driven and the emission-driven simulations is due to too much NOx in the model. Bill asked yesterday about heterogeneous removal of NOx. How is that handled?
Heterogeneous removal of NOx. I think, if at all, it's parameterized at the moment. So this might be a weak spot. Yes. No, I'm actually looking at the NOx in the model in the chemistry is certainly the next step to do, because I think that's where that's the main control over the methane sink, and we have to clarify that. Oh, Fiona just tells me there's no heterogeneous removal.
Okay. I see that as well. And there are a number of other questions in the chat, which I'm going to point you to, Gerd, if you could respond to people in the chat.
Yes, I will. Thank you.
Okay, many thanks. We'll go on to the next presentation, which is Adam Povey from NCEO and the University of Oxford. Are you ready to go, Adam? Adam, you may need to unmute.
It was ignoring me. Can you hear me now?
Yes, very loud and clear. Okay. Right.
Right, I'm ready to go.
Go for it.
So I'm Adam Povey from the University of Oxford. I'm coming at this in a slightly different perspective. I work on aerosol and cloud retrievals from satellites as my expertise. And so my job here is taking the aerosol component of the model, which we heard yesterday about how important that's proving to be in changing the climate sensitivity in the CMIP6 model set. I'm trying to look at the sort of outputs that UKESM is making and show that they're consistent with the sort of physical reality that we're seeing from space. This obviously has been done by models down the years. Usually I'd say though it's a relatively simple, though not wrong, comparison of just taking large averages and global things. So the plot you see here is from Jane's paper that's currently under review, showing along time, yearly average, and along the y-axis, the aerosol optical depth seen from a variety of different data sets. Whereas usually we just compare against one and go, oh, look, this average here is sensible to this average over here. In this case, on the black line, we have the UKESM ensemble. In red, we have the GC 3.1 ensemble, and then the other colors are different satellite data sets. And we see certain things like the purple lines from the Swansea algorithm falling right on the sorts of numbers we're getting out of the model, which makes us quite happy, whereas then getting MODIS in blue or some other European algorithms in green and yellow, giving it a different sort of magnitude. And this is somewhat common when you look at different aerosol data sets. They have a different magnitude of global aerosol optical depth. But the reassuring thing from this plot is actually the features are similar. In 1998, there was an El Nino, and probably from increased fires in the tropical Pacific region, you had a lot more AOD around, and that's being picked up in all of the data sets. And the broad element of these lines being pretty boring is common across all of these, which is handy. But we can do somewhat better than that in a comparison. We can firstly go to monthly outputs rather than yearly ones to get a bit more granularity, and we can also be regional. So these plots are from John Robson's paper under review about evaluating the North Atlantic from the UKESM. On the left, we again have time series for the same set of observations, though of course a different color bar, because we can never keep consistent color bars from paper to paper. There we see again 1998 picking up the El Nino. With the monthly resolution, we can see that there is actually a slightly different shape between the satellite data sets and the model, but nothing I'd be overly concerned about, though there is also an increased amount of AOD before that. Now that I'm less concerned about, because that's actually very early in that satellite's data record, and so actually that could just be an artifact from those earlier months. And this is the sort of thing where evaluating satellite data, there are always these tricky features that can come up. But actually I'm quite fond of the comparison here, where we see there's a relatively a flat AOD from sort of 2000 to about 2005, a feature in the middle there that's less well caught, but actually from 2008 onwards there's a slight decline, which is at the sort of level that I wouldn't expect satellites to pick up very up on, but the gradient is consistent across the different data sets and consistent within the UKESM. The only bit there really at the end of the figure we're showing here, around 2012, there's some sort of large maxima in AOD. I'll admit I don't personally know what it might be. There are plenty of these sorts of things that turn up, but that's not being picked up in the model. So there's a possibility that there's some manner of fire, some unique event that the model isn't representing there, rather than, I think, some sort of large-scale process. We can also do regional averages. So on the right-hand side, you see averages over the Atlantic basin. The UKESM is in the bottom right of that plot, and you see sort of a a dipole, for lack of a better phrase, of there being dust coming in the southern regions from the Sahara, and in the north there being a enhanced AOD from the North Atlantic storm track. That isn't picked up as clearly in the satellite data sets. There is a difference in there, but there's not as large a magnitude, or at least the bit in the middle isn't as clean in the satellite data sets. There's also more of a land-sea contrast there. And this is somewhere actually I think the model can inform the satellite data sets a bit more, because the model is showing us the sort of behavior we would expect to see in reality. But the North Atlantic region is cloudy and full of storms and can be difficult to run satellite retrievals in. We can go to even greater granularity by using a high temporal resolution run that was done for NCEO, giving hourly output of our aerosol observations. So these plots show along these are histograms, so along the x-axis we have aerosol optical depth on a logarithmic scale, and along the y-axis we have the frequency with which we see. Here, I've concentrated on some specific ground-based sites, a highly accurate sun photometer measurement, and then I've co-located daily average AOD seen from our various satellites and from the model. So the black line on both is the same, which is seen by that accurate ground-based sensor. On the left-hand side, we have a selection of NASA algorithms, which you can see broadly agree with each other quite well, as that NASA's good at that cross comparison. On the right-hand side, the purple line is the UKESM, and the green lines are a set of European algorithms. And the thing that's nice across a variety of these sorts of plots is actually it's quite difficult to distinguish the UKSM's distribution in these daily averages from the satellite data sets. You get features like the bottom left-hand plot. You can see the satellites have picked up one mode of a bimodal distribution and not the other. Whereas on the the bottom right, we have that element of the European algorithms are getting a better job. The UKSM rather smooths over what's potentially here a bimodal distribution. But again, we're looking at daily averages, and so that's not necessarily surprising. But I can but broadly, I've done, these take a fair bit of processing power, and some people may have seen these plots earlier in the year, and that was thrown together in a day, and I've put a lot more time into trying to make a better comparison here. And I'm still trying to work out simpler statistics that can summarize the contents of these plots in a manner where I can give nice global images just to get across ideas as to what sorts of features the model is doing well and which ones it's doing poorly. But it is interesting that the model is broadly within the sort of satellite elements. For a final way, thank you, of cutting into the fine details. So this is an exact co-location. So whereas the previous one was just looking at daily averages over a point, I'm now using those ground-based observations to actually finally subset the model. Rather than averaging every hour for the day, I'm just averaging those hours in which I had some observation on the ground. Obviously, we're not going to have replicated the exact reality from the model in the model, but this gives us sort of an idea as to what's going on. And in the bottom right hand corner, because we get the model, whereas the other ones are the different satellite data sets. And you can see again the model looks A, as if it's capturing that distribution of AOD from the ground-based sensor quite well, and B, it's capturing it about as well as any of the satellite data sets. The satellite data sets are obviously noisier because of the nature of the beast, but I'd say broadly, whereas the first global scale images I showed a year or two ago had elements of me seeing some features I was a bit concerned about, when you actually cut down to this higher temporal resolution product, I think you can actually get a surprising amount of confidence from a satellite person that wouldn't necessarily have believed that a model could do as well as a satellite seemingly. I've been quite pleased with this and hope to find the time and the mental energies to try and write this up into a report and give nicer statistics on what's going on there. So I think that's it for me for once in under my amount of time. Where's the chat button? I don't know.
Okay,
right.
Well, I've got the chat open, so I'll give you some guidance. So there's a comment and a question from Peter. It looks like 2012, oh, it's just popped off my screen. Looks like 2012 was a major fire year in North America. Could that be one of the contributing factors to the peak in AOD that you're seeing?
Quite possibly. As I say, the fact that the model hasn't picked it up, I would suspect that is something like fires or some sort of event that's encouraging emissions from unusual sources. I'll admit the El Nino one was, I'm not sure that's an El Nino. It was just chatting with people around a coffee table some months ago. It was pointed out that was an El Nino and a lot of things were on fire at the time. So yes, I wouldn't be surprised if that was an explanation.
Okay, and maybe just a comment from me. So the coupled model itself, of course, can't capture the timing of any given El Nino, but you could evaluate AOD in a sort of canonical El Nino minus La Nina context, satellite and model, and that might be a way forward.
Yes, it's elements of why I prefer the histogram-based comparison I show at the end, where by looking over a long period of time, you're just trying to see if the model captures the sorts of processes that happen in reality, rather than requiring it to exactly line up, which satellite simulators can clearly do some very good things, but I think you have to be a lot more careful about setting up the model and making sure you're comparing apples to apples.
Okay, question from Graham. He likes the histogram comparison that you've got up there, so do I, because the model looks good. Is it possible to use this to test the dust specifically, to look at, I guess, its specific aspects of the aerosol optical depth?
Yes, so the model does subdivide the different species, and most satellite data sets have some manner of differentiating between dust and not. Now the satellites, sometimes they vary on it's merely a coarse mode versus fine mode, and the satellites aren't as good as would be ideal at identifying dust. But yes, there is a hope to split this into more subdivided categories. It's just a matter of, in essence, changing which fields from the model I average before I begin running the code.
Okay, and a last quick one from me. I think the points you were referring to there in the analysis were quite polluted regions. So one of the key aspects of aerosol, of course, is to evaluate them in non-polluted regions. So are there any observations that you could do this in non-polluted regions? I know that's more of a challenge.
Yeah, well, so it's a matter, so those histograms at the end, those had actually been selected to make a different point. They were looking at idealized and non-idealized distributions. One was very log normal and one was very not log normal. Aeronet stations are distributed around the world. They are concentrated near universities due to the nature of maintaining instrumentation, but there are a few in more remote areas. There's also the marine aerosol network, which are observations taken from ships. There's a lot fewer of those, and they're harder to co-locate against, but there are other observations to look at. And yes, I would want to take, I do want to take a regime-based approach of not just looking at all the numbers in aggregate, because that unfairly samples the aerosol distribution globally.
Okay, many thanks. Have a look in the chat for a few more comments and questions, please, Adam.
Thank you.
And we're going to switch over, thank you, switch over to Paul Griffiths, NCAS, and I believe University of Cambridge as well. Okay, Paul, are you ready to roll?
I am ready to roll.
Okay, over to you.
Yeah, I'm going to be talking today about an evaluation of SMURPHS tropospheric ozone, so that I co-led and which is currently in discussion in ACP. I should thank my co-authors, particularly Lee Murray, who co-led the project, but also Fiona for leading the UK contribution to the AerChemMIP project, which has been really interesting to be part of. Also the UKESM team and Mohit and Luke for their outstanding technical support. And for the end, I'm going to be discussing some runs led by Sungbo and Jane Mulcahy, so I should acknowledge them now rather than forget at the end. You might ask, why tropospheric ozone? Well, it's an important atmospheric constituent. It's a greenhouse gas. It affects ecosystem function through its deleterious action on vegetation. It's an oxidant, so it controls greenhouse gas lifetime and affects secondary aerosol formation. And high levels of surface ozone are associated with poor health outcomes, so we need to take an interest in ozone in the future to understand air quality. It's formed in the troposphere from the oxidation of anthropogenic and biogenic VOCs in the presence of NOx, which makes it a challenging species when resolution and computational costs are an issue, and of course they're always an issue. UKESM1 compares well against observations. On the left you can see a comparison against the Simona Tilmes tropospheric ozone song compendium dataset, which shows ozone at various altitudes and locations as a function of time of year. You can see that the seasonal cycle is usually well captured, and that the agreement between model and observations is usually within the envelope of one standard deviation of the observations shown on the graph. On the right-hand side, you can see a comparison of UKESM1 tropospheric ozone column, not ozone as I've misspelled it there, where the contours are the OMI-MLS tropospheric ozone column, and the colours are UKESM1 ozone column as a function of latitude and time of year. And you could say that the seasonal cycle is good, but obviously our northern hemisphere summertime ozone maximum starts a bit too soon and goes on for a bit too long. And there's some high bias in the ozone column in the tropics, but the overall structure is pretty encouraging. In the CMIP6 experiments, the tropospheric ozone burden, the total amount in the troposphere, grows by about 40% from 1850 to present day, as shown in the bottom panel. You can see that the UKESM1 is the highest ozone burden in the 1850 times, and that CESM2 Wacom is the lowest. The growth of the ozone burden is initially rather slow, but then rapidly ticks up in the second half of the 20th century in response to rapid increases in anthropogenic ozone precursor gases at the surface, which are shown in the bottom right panels. You can see relative to 1850 that the largest changes are in the northern hemisphere, and that after 1985 there is a significant growth of ozone over East Asia. The lifetime of ozones is a few days in the free troposphere, which means that transport starts to mix ozone over longer distances, making anthropogenic tropospheric ozone an increasingly global problem. After 2015, we analysed the SSP 370 pathway, which is a middle-of-the-road scenario with good availability of data in the CMIP6 archive. And you can see that the ozone growth slows and eventually flattens off, probably in response partly due to the decline in ozone precursor gases after 2050 or so, but that's clearly not the whole story. If we look at the ozone tendency through the atmosphere, we can see that it's positive at the surface. Those are the red colours, close to the emissions of NOx. But of course, most of the atmosphere is NOx limited, so remote from emissions, the atmosphere turns over from ozone production into ozone loss. And you can see which reactions are most important for this process in the bottom right two panels, where I've shown the global integrated flux of ozone producing and ozone destroying reactions. You can see that these P and L terms are actually rather large. Their difference is small and positive, which I'll call net chemical ozone production. And in the middle panels, you can see how this NCP term evolves in UKESM1 and in the mean of the CMIP6 models. And this NCP term increases in 1950, crests at about 2000, and then declines as the anthropogenic ozone precursor gases decline themselves. The chemistry is only a part of the story, however. The deposition at the surface removes about 1,000 teragrams of ozone from the troposphere, and downward transport from the stratosphere brings in about 300 teragrams annually. So dry deposition is sort of balancing chemical production and downward transport from the stratosphere. Unfortunately, sadly, CMIP6 diagnostics and the data request don't contain any dynamical info about the mass flux of ozone from the stratosphere, so we infer this term by assuming the budget is closed and calculating a residual, which we identify with this stratosphere to troposphere transport. You can see that this residual does what we would expect. It declines in the second half of the 20th century as the stratospheric ozone burden declines, reaches a minimum about 2000 to 2020, and then starts to recover as the stratospheric ozone burden itself starts to recover. So we identify in the CMIP6 paper that the tropospheric ozone burden is under both chemical and dynamical control, and we hope to investigate this further in the future. The final thing that I'll say is that the AerChemMIP protocol adds an extra dimension to these CMIP6 runs. They feature a bunch of integrations in which emissions or some other atmospheric component is held constant at 1850 levels, and then the other forcings evolve along historical trajectories. You can see that these are sort of one-at-a-time perturbations that run in AMIP style models. So I think probably the one of most interest here is the green line in the right-hand panel, which is an experiment in which anthropogenic ozone precursors are held constant, 1850 levels, and everything else evolves along its historical pathway. And you can see that the ozone burden in the troposphere toddles along until we get to about 1970, when it starts to decline. We associate that with, as you might expect, a decline in downward transport from the stratosphere, but we can also use these individual one-at-a-time perturbations to attribute certain chemical precursor changes on the tropospheric ozone burden. And you can see that even though the ozone burden is declining, both chemical production and chemical loss are actually increasing over this time due to ancillary effects of increases in things like methane and lightning NOx. So there's quite a bit more work to do here, but in the interest of time, I will stop there. Thank you.
Okay, thanks, Paul. Right, there's 3 questions I can see in the chat. So the first one, surface ozone in the Arctic is poorly simulated. Does UKCA include halogen, in particular bromine, emitted from sea ice?
No, Shin. Is that a Shin question?
It is.
Yeah, no, Shin. We don't include bromine emissions from sea ice.
Okay. From Olaf in New Zealand. So Olaf's obviously pulling an all-nighter. Why does the stratospheric influx of ozone go to 0 around 2000? This seems inconsistent with other literature.
Yes, that's a unique feature of UKESM 1, I'm afraid, and we associate it with a strong stratospheric ozone depletion and an artifact that's probably introduced from difficulty in diagnosing where the tropopause lies. So we have some difficulties in calculating the individual terms, and we certainly have some difficulty in exactly closing the budget when each term is rather uncertain. So although that's a line, my guess is that's an envelope with a significant error bar on it.
Okay, and last one from Bill Collins. Can you get diagnostics from UKESM1 to check your residual equal STE?
Yes, in fact, the STE diagnostic was offline in the SMURPHS coupled atmosphere ocean experiments, but it's back online in the AerChemMIP experiments. And if you're interested, James Keeble and I have a nice paper where we look at the residual and the STE terms, and we show that they are actually pretty similar in UKCA version 7.3. So I think the answer to that is going to be yes. Okay, many thanks. Check the chat for any more comments, questions. One's just come in. I'm going to have to leave that for later. 2 have just come in. And I'm going to move over to Graham Mann. Graham, are you ready to roll?
Yep, I'm here, thanks.
Okay, over to you, Graham.
Okay, so I think I can control the screen to advance on one slide. There we go. Okay, so yeah, I'm talking about volcanic impacts on climate. So this is activity within the ACSIS multi-center long-term science program that Rowan was talking about yesterday a little bit, and so one of the activities is on volcanic impacts on climate. So this involves several people at Leeds and primarily also Oxford, Reading, and there's a component on satellite measurements also with RAL Space. But here I'm talking about the volcanic aerosol activity and volcanic impacts on climate. So I'm talking here about the climate response to volcanic forcings, and there's a coordinated multi-model activity within SMURPHS, specifically to compare the climate response to volcanic to the SMURPHS volcanic forcing among the different SMURPHS models. So if you can see my cursor here, yeah, there's different experiments within VolMIP to assess the short-term climate response and also the long-term climate response to a Tambora magnitude eruption. And here I'm going to be talking about the short-term climate response experiments And so the protocol is basically each model for this Pinatubo experiment on the short-term climate response are enacting the same volcanic forcing of the pre-industrial control in an ensemble that samples across the warm, neutral and cold ENSO phase, and also across positive, neutral and negative North Atlantic oscillation within the winter after the volcanic eruption. So this is specifically to understand the impact of those modes of variability on the climate response, and comparing the different models then to understand one thing specifically, that this influence from the North Atlantic oscillation is then to understand this observed feature after eruptions, where you see a winter warming over Eurasia and North America in the winter after the eruption, unusually. So this is a strongly dynamically linked effect, and so sampling then the models across these different modes of variability allows then to understand the variation and the specifics of that effect for specific eruptions. So yeah, at Leeds, myself and Wuhu Feng primarily has run the UKESM Pinatubo experiment, where we enact then the CMIP6 forcing and run these 27-member ensemble off the UKESM CMIP6 pre-industrial control. And what we're doing as part of this ACSIS activity is running a second 27-member ensemble. So we've done actually we've done a control ensemble and the volcanically forced ensemble to allow then all the effects that are going on in that pre-industrial stratosphere to play out and be identified across this range of variability. But now we're running a second pair of 27-member ensembles with what we're calling a microphysically consistent volcanic forcing for Pinatubo. So this is another an equivalent data set to the CMIP6 data set, but it's directly produced from interactive stratospheric aerosol simulations. So for the NERC highlight topic, on the historical hiatus and surge periods, we ran simulations for each of the three major volcanic eruptions in the 20th century, for Agong, for El Chichon and for Pinatubo, and have produced these microphysically consistent volcanic forcing data sets directly from those simulations, which are actually then back at the GA4 UKCA model. So these forcings are currently described in a paper in review in ACP discussions, where we and I'm showing here comparisons of the simulated aerosol optical depth here from interactive simulations of Pinatubo, comparing to the 6 data set and then the 2 alternative data sets from CMIP5. And so one of the primary things that the UKCA interactive Pinatubo runs resolve is then an evolving particle size consistently with the growth of the particles within this volcanic cloud, which you see here, for example, for 2 realizations of the eruption with 14 teragrams and 10 teragrams of SO2, comparing then here to the CMIP6 derived effective radius So I think I heard 2 minutes, two minutes there. So I'm just going to advance then to this last slide, which is illustrating on the left-hand side then the way we set up this this 27-member ensemble of the pre-industrial control. So what I'm showing here is the ENSO index on the x-axis and the North Atlantic Oscillation Index on the y-axis, and the colours here are then the QBO, essentially a QBO index, which is just the average zonal wind speed in the tropics, here shown for July to December. So this is then stratifying this ensemble across the different ENSO and NAO phase in the winter after the eruption, but by picking the blue points in each sector, we ensure we also effect an easterly QBO in our climate response experiments of the pre-industrial control. And what we can do is potentially contrast then a westerly QBO ensemble by sampling the red points here, where we're in westerly winds at 50 hectopascals. And here's just a comparison of the volcanic aerosol data sets from these microphysical runs with the interactive aerosol. Here I'm showing so these have been sort of converted to easy aerosol, waveband averaged extinction, absorption, and asymmetry parameter. And here I'm showing then a band in the mid-visible in the short wave, and then in the long wave, the absorption of outgoing long wave radiation by the aerosol. So this is one of the things with the that's my timer going up.
Yeah, could you wrap up, Graham, please?
With the microphysical scheme, the balance between these short wave and long wave radiative forcings is then consistent with the way the model is predicting the size distribution evolves. And we're basically encouraging people within the UK community there's a whole range of different responses that are affected in these runs that I think are a real resource for us in the UK to investigate.
Okay, thanks, Graham. We'll have to move on. I got just one quick comment. We know the QBO was a bit too long in UKESM 1, so we're hoping in the 1.1 release to improve the periodicity of the QBO.
In the pre-industrial control?
Just generally, in the model per se, we know the QBO is too long, the period. So we're looking to improve it.
I saw that in the pre-industrial, but I haven't seen how that changed.
Okay, so
thank you. Is there a question? Something like that.
Hello, can you hear me?
Hi, I think, have we lost Colin? Let's move on then. Thank you very much for that, Graham. We'll move on to Lee Demora next. So you should have control, Laura. Lee, over to you.
All right, thanks. Okay, so just to put this into context, it's a bit different from the rest of the talks we've heard today. So this is actually, again, my talk is titled Earth System Music, the Creation and Reach of Music Generated from UKESM 1 Data. So yeah, so putting it into context, we attended as you know, we attended the Blue Dot Science and Music Festival in the summer of 2019. And we had all this wonderful interactive stuff for people. We had the globe and we had some toys and videos and things, but we didn't actually have any music, despite it being a music festival. So we decided to investigate whether it'd be possible to make some interesting music from our model. And yeah, went ahead and did it. The two main points that I hope to transfer across from this talk is that it's increasingly important that we engage in non-experts in our model results, but also our methods. And the second point is that it's also increasingly easy for scientists to use social media to interact with non-experts and wider audiences. So musification is basically the process of turning non-speech audio to using non-speech audio to convey information. And when you, so the most well-known scientific example of this is the Geiger counter, which emits a click in the presence of ionizing radiation. So almost all scientific data we've seen today was visual, which isn't always helpful for visual learners. And this kind of sonification can sometimes help with visually impaired people or auditory learners. And it can sometimes be easier to perceive rates of change and patterns and repetitions and that kind of thing. So what we did is we created a series of pieces. There's currently 8 of them in the portfolio at the moment based on UKESM ocean data. And with the idea being that it covers a wide range of modeled data, behaviors, but also a wide range of methodologies. So we include things like the spin-up, the pre-industrial control run, historical runs, future scenarios, and allows us to sort of demonstrate all the different tools that we use to make models. So the way that it generally works is that the notes track the data. So if the data goes up, then the pitch of the note rises as well. And then those data are then modulated within a requested scale. So this first piece that I'm going to play for you in a moment is the Earth System Allegro. It's modulated it to be C, G, A minor, F, so the famous 4-chord song. You'd recognize it from things like Let It Be by the Beatles, No Woman, No Cry by Bob Marley, Africa by Toto, or With or Without You by U2. It's a very common 4-piece song. So I chose this one so that it would feel familiar, it wouldn't alienate too many people. And it's also sort of happy major chords. So the data set we used here was the historical and the SSP 1.9. So it's the gentlest possible greenest climate change future. So I should be able to click here, and you may want to adjust the headsets if it's too loud or too quiet here. Yeah, so that was the first piece that we made, and it kind of introduces the concept in a gentle, friendly sort of way. So the way that we produce these is we take the UKESM model data in its CDFs, we run it through the BGC val, it's a Python-based evaluation toolkit we use to monitor the spin-up and the historical runs, and well, and other runs as well. So that produces these time series data sets. From there, we have a series of settings for the musical processor. So what range to set the notes to, very artistic choices like the tempo, the set of chords, the scales, and so on. So we load the data, we apply a smoothing effect so that it doesn't jump around too much if we want that effect. We convert the data into MIDI pitches. So MIDI is a musical interface, musical instrument device interface format for musical data. And it uses a series of values between 1 and 127. So we basically fit it into that range of integers between 1 and 127. Then we enforce the choice of scale or chord. We set velocities, and what that means is that's the how loud the piano key is hit, how hard it's hit, so how loud the note gets. We remove duplicates. So if 2 notes are played successively, then the length of the first note is extended and the second note is removed. We then extend the final note at the end and save it as a MIDI file, produce some images, and then pass it through the Timidity piano player, which is a synthesizer. Then convert it into a video and put it on YouTube. The PDF sheet music is also available, but that's the process, and it's fairly straightforward. just to highlight the musical decisions here as well. So that's what makes each piece unique. So these are the creator has some kind of choice to make, and that's me and a discussion with other people in the authorship team. So we typically, well, in this example, this is the notes that the keyboards would use for that piece, showing the chord C major. So the Drake Passage Current, you can play the C major chord, and then the other three, sorry, it plays the scale of C major, and then the other three datasets play successively lower notes inside the chord. And so that's what gives it the musicality. So we also have the choice of the pitch range, so how far left or right on the keyboard each note goes. The tempo, the number of beats per note, the key, the choice of instruments. I produced 7 pieces for piano, but recently I've started using other instruments. The style, there's also mastering effects, delays and reverbs. And these choices combined together allows us to sort of attempt to imbue an emotional context into the piece. For instance, the previous one was SSP 1.9. So we try to have that optimistic and free sounding. Whereas if we're looking at SSP 8.5, we may want to have sort of try to imbue it with a sense of foreboding, for instance. And so that's kind of how the artistic decisions work. I seem to have lost control here. Can I? Oh, there it is. Okay. And so we also, so once we published these pictures, I shared them on my social media networks and various other places, and made an attempt to quantify the reach. So within the first 90 days, we had 500 views and 465 watch times, and the earliest publications would have been at the end of last summer. So now, you know, several months later, we have 2,500 views and 35 hours of watch time with lots of positive comments. And so we're quite happy with where this sits. If you look at there's one other video about UKESM on YouTube, and then I believe it only has 200 odd views. So we've already smashed that. The most popular YouTube video with Earth system modeling, I believe, only has 5,000 views. So 2.5 isn't so bad if you put it into that context. I mean, okay, thanks. Yeah, obviously, we don't really, you know, have the millions of subscribers that some of the big channels do, but we still are reaching a fair number of people. There'll be lots of people have made lots of great suggestions on ways that we could extend this. It would really be nice to have a live performance. We actually had a couple lined up that were made impossible by the COVID outbreak. I've started adding additional instruments. There's a string quintet that has been produced recently. There's some additional musical styles would be nice as well. Using the work on ESM Val tool, I plan to add additional models into musical pieces. Maybe different parts of the UKESM system would be nice instead of just the ocean. And it would be really good to have like higher quality visual stuff. I'm very much on the auditory side and less so on the visual, so it'd be good to make a nicer looking video. But yeah, I just wanted to show this as a pilot study, and there's a manuscript coming in Geoscientific Communications soon. Thanks a lot for listening.
Cool, thank you. I've had a few people drop out. Colin's back. Okay, cool.
Rob, now. Yeah.
Colin, can you see the questions in chat, or do you want me to ask them?
I can quickly ask them, yeah. So cool. If people did notice, a few of us got booted out there, so I'm afraid I missed all your talk, Lee, but I've heard it before, so I'm sure it's fantastic. There are 2 questions in the chat. I'll ask them quickly and you can respond, and then we'll go to coffee. How do the musical choices affect emotion? Is it more than the choice between major, minor, slow, and fast? From Jeremy. And then Doug also asks about stretching from audible to visual, which you just mentioned.
Okay, so in terms of imbuing musical context, it's a very sort of loaded question because, of course, different cultures experience music differently. So, I mean, I've very much come from the Western tradition here where major is happy and minor is sad, and fast is happy and slow is sadder. So that's kind of the tradition. But I've spoken with Ranjini about, for instance, looking at Indian classical music, where they have a very different musical structure and very different emotions attached with different sounds. So it'd be quite interesting to explore that on the musical side. I don't know if that answers the question. But.
Right, and Andrew just said that he did ask a question. Obviously, I didn't see it because I got bombed out of the system. Rob's put it up. Would it be possible to illustrate how the separate components going into an aria affect it? that might make it easier for someone who's tone deaf like me to understand how, say, CO2 uptake appears in the final piece.
Yeah, I think that this is confounding two issues. One of the things is really that when all the parts are played by the same instrument, in that case the piano, it makes it very difficult to separate the different parts and link them together. Whereas I have another piece that I've produced here in the bonus slide, which is a string quartet, which links different instruments with different parts. So it makes it easier to separate them, if that makes sense. Right. If you can tell the difference between a double bass and a violin, for instance.
Okay, which Andrew claims he can't, but we'll find out if you run it. Okay, and with that, I think we're going to go to coffee then. So thanks, Lee. Apologies that I dropped out. It seems I was not the only person. So it may have been a Metalfis IT problem, but we're back. Right, we are starting again at 11 o'clock sharp, so you need to be online a couple of minutes before 11 o'clock. So you have roughly 20 minutes maximum to knock up your coffee, drink it, and be back, please. Is there anything you want to add, Hazel, if you're online, or are we just coming back at a few minutes to 11?
No, that's fine. Sorry, somebody's controlling my cursor.
Well, that would be me.
Let go.
We mentioned that we'd just leave them playing during the break?
Yeah, that's right. We'll leave the music playing now.
Right, so people can have their coffee and listen to the music at the same time. So
yeah.
Back a couple of minutes before 11, please. Thanks. Thanks to all the speakers.